Maybe Adam is the most famous and popular optimizer in deep learning research. So Adam is momentum method plus RMSProp algorithm. It's kind of. So Adam algorithm iteratively compute the momentum vector and the RMSProp the gradient scale vector GT. So the momentum vector, as before, just update the momentum vector using the first order derivative gradient of your loss function f at point xt with moving average coefficient eta 1. So that multiply eta 1 to the past history and multiply 1 minus eta 1 to the current history, current gradient vector. So when this value close to 0, then your momentum vector just rely on the current gradient vector. But this value, when this value close to 1, then you basically keep almost every information of your past history. And this one as well. So you have a different coefficient eta 2, different parameter eta 2, and you iteratively update your moving average for the second order gradient. It's the second order, it's the scale of gradient vector. Okay, so this is secant momentum. So the bias corrected version of first and second order second momentum method is this. M hat t is equal to mt over 1 minus s1 eta 1 power to t, and g hat t is equal to gt over 1 minus eta 2 power t. So why we have to multiply and why we have to divide the original momentum vector mt and gt. So basically, when you set m0 equal to 0 vector and g0 also equal to 0 vector, m1 is eta 1 times 0 plus 1 minus eta 1 gradient of fx1, right? m2 is equal to eta 1 times 1 minus eta 1 times gradient of fx1 plus 1 minus eta 1 gradient of fx2. m3 is equal to eta 1 square 1 minus eta 1 gradient of fx1 plus eta 1 or minus eta 1 gradient of fx2 plus 1 minus eta 1 gradient of fx2. So at this time, when you add all the coefficient in front of your gradient vector, sorry, this is gradient of fx3. So for this time, you have only 1 minus eta 1. For this time, you have eta 1 times 1 minus eta 1 and 1 minus eta 1. So for this time, the total coefficient in front of your gradient vectors is 1 minus eta 1 plus times 1 plus eta 1. Okay. For this case, you have these three coefficients, and the total summation is 1 minus eta 1 times 1 plus eta 1 plus eta 1 square. Okay? And this is equal to 1 minus eta 1 square. And this is equal to 1 minus eta 1 power to 3. So the total coefficient in front of gradient vectors. For m1 is 1 minus eta 1. For m2 is 1 minus eta 1 square. For m3, this is 1 minus eta 1 third. By mathematical induction, you can easily find out the total coefficient in front of your gradient vector for mt is 1 minus eta 1 part 2t. So to make the sum of coefficient equal to 1, you just need to normalize mt vector by this constant 1 minus eta 1 part 2t. Likewise, analogously, you can compute the total coefficient in front of the second momentum, and when you normalize by 1 minus eta 2 part t, then again you have total coefficient is equal to 1. Okay, so m hat t and g hat t have this meaning. And Adam update rule basically just combine momentum method and RMSProp. You update your parameter xt plus 1 is equal to xt minus your step size gamma over square root of g hat t plus epsilon, which comes from RMSProp, and not gradient, but you use the momentum vector m hat t. Okay, so Adam method take the two benefit from momentum method and RMSProp idea. You take the momentum averaging idea so that your zigzag behavior cancelled out if you have very high movement towards some one particular direction, and that direction make a zigzag behavior. And also the momentum method have very nice property with a stochastic gradient descent algorithm, which can cancel out the noise movement. And RMSProp algorithm also very nice property. From the second momentum of your gradient vector, you can roughly guess the curvature, shape, and the stiffness of each direction. So by normalizing your stiffness, you can expect more regularized contour, your loss surface, and you can converge to local minima more easily and much faster. So this is not just very not only just very simple idea, but also it provides very nice practical achievement. In many scenarios, Adam algorithm outperform existing stochastic gradient descent approach. And nowadays, Adam algorithm is kind of a default gradient descent technique. So when you design a new deep learning architecture, just try Adam. Most of the time, Adam performs very well.